Okay, so this time, so far, this is what we were doing. Second order, linear, constant coefficient, homogeneous differential equation. That's what we are doing so far. And as I told you, every time you remove one of these conditions, it gets harder, right? So the reason we have such a long name is because we want to be very specific. More specific you are, the narrower your class of differential equations you're working with. So because you're not working with a lot of different ones, it gets easier.
That's what we just did, right?
This is what we did so far. But now I'm going to introduce to you this one. So I'm going to get rid of the homogeneous. So we will try to do second order linear constant coefficient differential equation, possibly not homogeneous. How do you deal with such a thing? Okay. So let me show you an easy example. Example 1. Let's make it very simple. Y double prime minus y equal to, say, what should I do? E to the 2x. Something like this. Let's try to do that. As you can see, the left side is second order linear constant coefficient as before. The only difference is now on the right side you have some function of x. How do we deal with that? But once again, are we trying to solve it? No, we're trying to make good guesses. Okay? We're trying to make up some nice guesses that will satisfy this differential equation. All right, so we're going to try this. I'm just going to think about one solution that could satisfy it, just like before. What kind of function can you plug in on the left side that could produce the right-hand side? E to the x? Okay, well, that's a good start. If you plug the e to the x on the left side, what would you get? Second derivative of e to the x is? E to the x minus another e to the x, you get? 0 on the left side, and that's not going to create e to the 2x. So does anyone have any other ideas? What do you want to plug in? No, come on. Just think about another function that you can plug in and get something similar to right.
Cosine x.
2e to the 2x?
Cosine.
2e to the 2x? Okay, let's try 2e to the 2x. I like that.
Yeah.
Okay, by the way, cosine is like totally wrong. How can that work? Like, cosine, if you differentiate twice, you're going to get another cosine, and then cosine. You're going to get cosine on the right side. So that's totally ridiculous, right? So, but I like this. So let's try. Let's try.
We weren't that far off.
2e to the 2x. Okay. Let's see if this works. Okay. If I say y is 2e to the 2x, what's y prime?
4e to
2x.
4e to the 2x. And then what's y double prime?
8e to the 2x.
And then you plug into the left side, what do you get? 8e to the 2x minus 2e to the 2x because you have y, right? And then if you compute, what do you get?
6e to the 2x.
You get 6e to the 2x. And hey, I mean, it didn't work, but at least it created something quite similar, right? E to the 2x, e to the 2x. I mean, maybe if you can change this number to something, it might work, right? Are you convinced that we could make this work if I change some number here? Okay.
Yeah.
And that's when you get a little more smarter. So first you try this, and then say, okay, now I'm going to try the following one.
Negative.
Why not try y equals to a times e to the 2x? So a is some constant that I'm going to figure out later. Just just pretend that there's some constant here that we're going to figure out later and plug it in, right? So if y is a times e to the 2x, then what's y prime?
2a e to the 2x.
Thank you. By the way, the person who just said it was Dylan Warren. It was good, right? Correct answer. Okay, what's y double prime? 4a e to the 2x. And David just told me what that was. Thank you. All right, and then you plug it into the left side. You get y double prime minus y. This was the left side, right? And that's equal to 4a e to the 2x. And then minus a e to the 2x. And what's that? 3a e to the 2x. And what do I need this to equal to?
1/3.
E to the 2x. Therefore, what should the value of a be?
1/3.
1/3. If a is 1/3, then I have a single solution. Alright, so we found out that y equals to 1/3 of e to the 2x will satisfy this differential equation y double prime minus y equals to e to the 2x. Okay, now we found just one solution, but we know this is the second order differential equation, so we should be finding infinitely many solutions, actually a general solution with 2 free parameters. That's our goal, right? So if we found that one solution, how should we find the other solutions? Hmm? What do you do?
Yes, again.
Huh? What do you do?
Like we've been doing?
Like what?
Cosine.
Alright. Okay. So I was expecting something like C1 times 1/3 e to the 2x, something like that, but that wouldn't work. It wouldn't, right? Taking C1 times that would just give you another C1 on the right side, so it can't work. And here is the wonderful idea. The wonderful idea is that if I have the solution to y double prime minus y equal to 0, then I can figure out what's going to get killed when I calculate the left side, right? So let me explain what I mean by that. Just but before explaining what I mean by that, let's try to figure this out. Okay? What's the solution to this? R squared minus 1 equal to 0. R minus 1 times R plus 1 equal to 0. So you get R equals to 1 and negative 1. So what's the general solution? Y equals 2. What's the general solution? C1 e to the x plus C2 e to the negative x. Alright, so I know that if I plug these guys on the left side, it's going to go away. Right? And the wonderful idea is to take this solution of the homogeneous equation and add the one solution we found. Okay? We add these two. So here's the idea. The wonderful idea is to take y as the particular solution that we found, this one solution that we found, and add to it this complementary solution, which is the solution of the homogeneous differential equation. Okay? Now, why would that work? I'm claiming that if you add them, you get the general solution. In other words, I'm claiming that if I do 1/3 e to the 2x and add to it C1 times e to the x plus C2 times e to the negative x, in the left side, it's going to create e to the 2x and it'll be the general solution. Why would that work? Do you see it? Do you see that it's going to work? Because if you plug this entire thing on the left side, this one will get calculated and get subtracted, and what's this going to create? Either 2x as you want, right? But this one, sadly, all these guys, when you plug into the left side, it's all going to get killed during this differentiation and minuses, and it just goes away, right? Yeah. So these guys are lost. Oops. Yeah. These guys are lost when you plug into the left side, and therefore you know that when I plug this entire thing on the left side, it's going to create exactly the right side. Okay? So that's the great idea of dealing with the homogeneous differential equation. So actually this is the answer. This is the answer. And we may summarize it as following. So how to deal with a non-homogeneous differential equation. Okay? So first, step one, you might say, find one yp, just one yp. Just do all you can. Just try to mimic the right-hand side and see what could produce things on the right side, and just use your imagination. Just try something. Okay? Just get one yp. Okay? You don't need to get all. You just need one yp. Just make good guesses. Okay? And once you make them, then y is just yc plus yp, where yc is the solution of the homogeneous differential equation. So, and because we know how to solve the homogeneous version, if we know that, then we can just add the yp, and that's the general solution. Yeah. You want to see something here? Okay. All right.